Hello friends, in this video we are going to discuss about equation of motion of a plasma. If we are considering plasma, we have to consider electromagnetic as well as fluid motions also, because a typical plasma density might be of 10 to the power 18 ion electron pair per meter cube. So it is not possible to trace the individual trajectory of each particles. So whenever we define plasma, we use two equations. One for the normal equation, which is equation of motion for electromagnetic particles, which depends on electric and magnetic field both, and we use some fluid equations also. In the fluid approximation, we consider the plasma to be composed of two or more interpenetrable fluids. In the simplest case, when there is only one species of ion, we shall need two equations of motion, one for the positively charged ion fluid, one for the negatively charged electron fluid. In a partially ionized gas, we shall also need an equation for the fluid of neutral atoms. The neutral fluid will interact with ion and electron only through the collision. The ion and electron fluid will interact with each other even in the absence of collisions because of electric and magnetic field they generate. Now we will derive the equation of motion of a plasma. For this, let the density of electron is given by small n, mass of the electron is given by small m, charge is negative E, the drift velocity is small v, and the temperature is capital TE. Similarly, for the neutral atom, the charge and drift velocity is 0, but their masses are almost equal to the masses of ions. The equation of motion of any particle is written as in terms of rate of change of momentum, which is equal to the force. If the mass is m, velocity is v, then the force is given by m del v over del t is equal to vector F. If the particle has electric and magnetic field, then the force acting on it is given by F is equal to minus E dot E minus E v cross B. So this equation of motion is given as m del v over del t is equal to the minus E dot E minus E v cross B. So this equation describes the electromagnetic behavior of plasma. In addition to this, we will requiring the Maxwell equations, but to include the effect of fluid motion, we have include some other terms. Rather than the electric and magnetic field, we will include the other terms one by one. First is collisional drag. We consider any one as such a random motion in which any electron having the mass m and the velocity is v, which is coming in the vicinity of another charge, and the trajectory of the particle is being changed. Now, if the particle is very far away from the another charge, then there will be no change in the trajectory of particle, and the change of momentum will be 0. If the particle comes closer to the another charged particle, then momentum is mv, and the change in the momentum, which is given by mv minus mv, is equal to 2mv. The average change in the momentum is given by 2mv by 2, which is equal to the mv. The change in the momentum per collision is mv. Now, if there is new collision per second, then the change in momentum loss in new collision is given by mv into nu. But this momentum is decreasing the speed of the particle. So we can write in terms of force, F collisional drag is equal to minus mv into nu, and nu is the collisional frequency. Till now we have supposed that the center of the particle are fixed. Now if the velocity of incident particle is vi and the velocity of the particle due to which the momentum is changing is v, then the resultant velocity is given by v minus vi. Then the force will become F is equal to minus m nu into v minus vi. If we include the impact of collision drag in the equation of motion, then the term of the collision drag will also be included in the equation of motion. Now we will take another effect, that is because of partial pressure of the electron. The pressure exerted by a gas on the wall of its container is known as partial pressure. Since gas have lot of molecules, due to the momentum of these molecules, there have lot of collisions. The number of collision increased, the partial pressure will be also increased. As the temperature will increase, the velocity of the molecules are also increased. Due to this, the number of collision will gets increased. As the result, the partial pressure is also increased. By this approach, the partial pressure exerted by the electron Pe is given by Pe is equal to nkBT, where n is the number of electrons per unit volume per charge density. Kb is the Boltzmann constant and T is the temperature of electron, and the P is n into Te, where Kb is hidden in the Te. The partial pressure depends on the number of particles included in the volume. Suppose we have given a plasma and we take a small volume element. Suppose the surface area is unity and the width is delta x, as you show here. The width is delta x and the surface area is unity. By this, the volume of the element can be written as 1 into delta x is equal to delta x. The number of particles in the volume delta x are n into delta x. Suppose the particles are colliding on the wall of the element and exerting the pressure P in the x positive direction. Similarly, the particles on the other side are colliding in the negative x direction. But the motion of the electron is not uniform, so the density will be also variable. Due to this, the partial pressure will also be variable by delta Pe, and the net partial pressure we can write Pe plus delta Pe. The net force on the considered volume element is minus del Pe x cap, where x cap showing the x direction. Now the force per unit particle, which is given by minus del Pe by n dot delta x x cap. Substituting the value of Pe, which is equal to nte, we have earlier derived Pe is equal to nte in the equation. Then the force will become vector F is equal to minus 1 upon n del over del x nte. Now the equation of motion becomes vector F is equal to minus E dot E minus E v cross b minus mv nu minus 1 upon n nte. In this equation, the first term represents the force due to the electric field, second term represents the force due to magnetic field, third term represents the collision drag we have earlier derived, the fourth term which is the partial pressure exerted by the electron. The velocity field is dependent on the two things, position vector and the time. And the equation vector F is equal to minus E dot capital E minus E dot v cross b minus m v into nu minus 1 upon n nte represent the equation of motion of a plasma. As the velocity field is dependent on position and time, so we can write del v over del t is equal to the partial v by partial t plus v dot del into vector v, where v dot del is the convective derivative. Here we have a concept of convective derivative. A convective derivative connects the partial time derivative to the total time derivative, and it is defined as a dot product of velocity, and it is a scalar differential operator. Using the convective derivative, we can write the equation of motion of a plasma in the form of m partial v by partial t plus v dot del into vector v is equal to the minus E dot E minus E v cross b minus m v into nu minus 1 upon n del into n dot te. This equation represents the equation of motion of a plasma in terms of convective derivative.